So in continuing with stoichiometry, today we'll be talking about limiting reagents. So in the previous lecture, we looked at reactions that only we knew the mass of one of the reactants, the other one was in excess. Now we're going to be looking at what happens when reactants, both information about both reactants are given. And just a couple of easy steps that we use for limiting reagent problems. A lot of this we've already done when we talked about stoichiometry the previous lecture, but just to kind of recap. So of course you always need a balanced chemical equation, because if your equation is not balanced, then you don't get the right mole to mole ratios. And then you need to convert the reactants to moles. So if you're given mass of reactants, you would convert it to moles, and then use the mole ratio to convert it to moles that you want. So that's in step 3. So once we convert all the reactants to moles, we convert it to moles of the product that we want, and then we see which one produces the smallest amount of product. That's going to be our limiting reactant. And based on the limiting reactant will tell us how much product is produced. So once you know which reactant is the limiting reactant, then we take the moles of product produced by that limiting reactant, and in some cases you can calculate and find out how much of the excess reactant is left over. And so the amount of product produced by the limiting reactant is called theoretical yield, and we'll be talking about that throughout this lecture. So here we have an example. We have how many grams of solid aluminum sulfide can be prepared by a reaction of 10 grams of aluminum and 15 grams of sulfur. And we can disregard the how many grams of excess reactant is left over. We're not going to be talking about that in this lecture. So unlike the last lecture, here we have the mass of aluminum and the mass of sulfur in this chemical reaction. So first we're going to go through kind of a flow chart of how we solve a problem like this, and then we'll work out the numbers. So of course we need a balanced chemical equation. Just like we did in the last lecture, we're going to take the mass of aluminum and the mass of sulfur and convert them to moles of each. So we're still doing mass to moles. Then we use the mole ratio to convert it to moles of product. And here aluminum sulfide is the product that we want. Then once we find the moles of product, we see which one produces the fewer or least amount of moles of product, and then we convert that to mass to get the theoretical yield. So this is referred to as the theoretical yield. So again, when we find the moles of product produced by each reactant, we're going to look at those two numbers and see which one is the lower one, and then whichever one is, that tells us what the limiting reactant is, and then we take that moles and we convert it to mass of product. So anytime we're dealing with stoichiometry, if we're given mass, we're going to have to give the mass of product, or the amount of product, in mass as well. And this is referred to as the theoretical yield. It's the amount of product produced by the limiting reactant. And this is the same pattern we're going to be doing over and over when we're doing limiting reagent problems. We're going to take the mass of each reactant, convert it to moles, use the mole ratio to convert it to the moles of product we want, determine which one is the lower number of moles, and then we convert that to mass to get our theoretical yield. Every problem we do, we're going to be doing these steps. And no, don't worry about excess reagent. We're not going to be doing that in this lecture. So now to see it worked out. So the balanced chemical equation is given to us. So aluminum plus sulfur gives us aluminum sulfide. So what this means is that 16 moles of aluminum produce 8 moles of aluminum sulfide. So if we were to write the mole ratio, or the equality, it would be 16 moles of aluminum equal 8 moles of aluminum sulfide. We get that from the chemical equation, the balanced chemical equation. And then we have 3 moles of S8 equals 8 moles of Al2S3. So again, these are the two we're going to need because we're going to convert to aluminum sulfide. Again, we're disregarding the excess reactant in this example. So now we have our mole ratios. We need to set up our conversion. So here what we're doing is for aluminum, we're taking the grams of aluminum, dividing it by its molar mass, which we get from the periodic table, multiplying it by its molar ratio, and we get to do the same thing for sulfur, and we get the moles of product produced by each reactant. And so here's where you ask yourself, which one is the lower number or fewer number of moles of product? And the answer to that in this case is sulfur. So sulfur is the limiting reactant. Then we convert that to mass, and we get that the theoretical yield is 23.4 grams of aluminum sulfide. So again, this is referred to as the theoretical yield. So this is the total amount of product you can form if you reacted 10 grams of aluminum with 15 grams of sulfur. So again, we took the mass of each reactant, converted it to moles, multiplied it by the mole ratio to get the moles of product produced by each reactant. Since the one produced by sulfur is the lesser amount, sulfur is the limiting reactant. And then we multiply by the molar mass of aluminum sulfide to get the theoretical yield. So this is the best we can do. If we did this reaction perfectly, we would get produced 23.4 grams. We don't worry about the excess reagent in this example for now. So here we have another example. We have the reaction of B2H6 plus H2O gives us H2 plus H3BO3. And if we use 86.5 grams of B2H6 and 70.5 grams of water, how much H3BO3 is produced? Oops, wrong button. So here we're given the amount of both reactants. We want to know how much product is produced. And we're interested in this product, H3BO3. So we don't worry about H2. We want to convert the reactants into moles of H3BO3. And before we do that, we have to check to see to make sure that the equation is balanced. That's step number 1, is make sure we have a balanced equation. And so when we look at this, we notice that we have 2 boron, write it over here for the reactants. We have 8 hydrogen and 1 oxygen. So that's on the reactant side. On the product side, we have 1 boron, 5 hydrogen, and 3 oxygen. So now nothing is balanced, but the first step, what we want to do is balance the boron because it's the non-hydrogen oxygen element. So to balance the boron, we're going to need to put a 2 in front of H3BO3. So again, that 2 gets distributed to the H, to the B, to the O. And so now the number of boron is now 2. The number of hydrogen is now 8. And the number of oxygen is now 6. So you notice now that the boron and the hydrogen are balanced. There's 2 boron on both sides and there's 8 hydrogen on both sides. But the oxygen is not balanced. On one side we have 6, on the other side we have 1. So in order to make this 6, we got to put a 6 in front of H2O. And again, this gets distributed to the hydrogen and to the oxygen. So now we have 6 oxygen, but we have a total of 18 hydrogen. We have 12 from water and 6 from B2H6. But on this side, we only have 8 hydrogen. And we don't want to put a coefficient, another coefficient in front of H3BO3 because that's going to mess up the other balanced elements. So we want to put a coefficient in front of H2 in order to balance the hydrogen. So there's 6 hydrogen from H3BO3. To make it 18, we're going to put a 6 in front of H2. So now we have 18 hydrogen. So the coefficients are 1, 6, 6, and 2. So now we're ready to convert the mass of each reactant into products, into the product H3BO3, determine which one is produces the fewer moles of product, and then convert that to mass. So I'll set up my train tracks. We're going to be doing the same thing twice, so I'm going to put 2 sets of train tracks. So in the first one, we're going to convert B2H6 to moles of H3BO3. And again, we're starting with the mass of B2H6. So we need to divide by the molar mass. So we'll calculate that over here. So 26 goes on the bottom. One mole goes on top. The next step is we want to convert it to moles of H3BO3. And if we notice here, the coefficient in front of B2H6 is 1. The coefficient in front of H3BO3 is 2. So it's a 2-to-1 ratio. So 1 mole of B2H6 equals 2 moles of H3BO3. So now since we're starting with B2H6, it goes on the bottom. And then 2 moles of H3BO3 on top. And we're going to do the same setup for H2O. So we have 70.5 grams of H2O. We need the molar mass of H2O. So again, since we're starting with mass, to get the moles, we divide by the molar mass, so the grams goes on the bottom. So 18 grams. Now when we look at the mole ratio, there's a 6 in front of H2O and a 2 in front of H3BO3. So the mole ratio would be 6 moles of water equals 2 moles of H3BO3. So since we're starting with moles of water, it goes on the bottom in our conversion to moles of product, and H3BO3 goes on top. Now we can plug and chug. You multiply everything on top, divide by everything on the bottom. So you'll notice here that water produces the fewer moles of H3BO3. So what that tells us is that water is the limiting reactant. So since water is the limiting reactant, we don't need to worry about B2H6. So we can disregard everything from B2H6. We're just going to focus on water, and now we know that the moles of product produced by water is 1.31. So now we're going to convert this to mass of H3BO3. Again, once we determine the limiting reactant, we disregard everything for the other reactant because we no longer need that information. So now we're going to convert it to mass of H3BO3. So we need the molar mass of H3BO3. We get 59. So now we're going to convert moles to mass. Mole goes on the bottom. Mass goes on top. We get 77.3 grams. So again, this is referred to as the theoretical yield. So here we have this reaction. We want to know what is the theoretical yield of chromium that can be produced from a reaction of 40 grams of chromium 3 oxide with 10 grams of aluminum according to the chemical equation below. And it says it's unbalanced. So the first thing we need to do is balance the equation. Sometimes it'll give you balanced equations, sometimes it won't. So we have 1 aluminum, 2 chromium, 3 oxygen. On the product side, we have 2 aluminum, 1 chromium, 3 oxygen. So you notice here that the chromium and aluminum are not balanced. On the product side, we have 2 aluminum. On the reactant side, we have 1 aluminum. On the reactant side, we have 2 chromium. On the product side, we have 1 chromium. And you'll notice that both aluminum and chromium are by themselves. So this is a very straightforward one to balance. To balance the aluminum, we need to put a 2 in front of the aluminum. And to balance the chromium, we need to put a 2. This is the balanced chemical equation. And so what we're going to do is we're going to convert the mass of each reactant into mass of chromium. And again, the reason we chose chromium was because that's what the problem stated that they were interested in. So the mass of each reactant is going to be converted to moles of chromium to see which one produces the fewer moles of chromium. So again, we're going to need some molar masses. I'll go ahead and do those. So molar mass of aluminum, 27 grams per mole. Molar mass of chromium, 52 grams per mole, and then the molar mass of chromium 3 oxide. 152 grams per mole. So these are the molar masses of the reactants and products. That's one thing we're going to need. The other thing we're going to need are the mole ratios. So for aluminum to chromium, you see 2 moles of aluminum equal 2 moles of chromium. And we notice 1 mole of Cr2O3 equals 2 moles Cr. This is all what we need to do this problem. So I'm going to go ahead and draw 2 sets of train tracks. So first we're going to do aluminum converted to chromium. So we have 10 grams of aluminum. Since we're starting with mass, to convert it to moles, we divide by the molar mass. Now we use the mole ratio. Since we're starting with aluminum, it's going to go on the bottom, chromium goes on top. We're going to do the exact same thing for chromium 3 oxide. First, we're going to convert it to moles by dividing by the molar mass. And then we're going to convert it to moles of chromium. So now we have our equation set up. We can solve for the moles of product produced by each reactant. And so you'll notice here that aluminum forms the fewer moles of product. So aluminum is the limiting reactant. So that means we can disregard everything about Cr2O3. Don't have to worry about that anymore. Disregard it. And now we can take the moles of chromium and convert them into mass of chromium. So mass goes on top. mole goes on the bottom. We get 19.2 grams chromium. And again, this is referred to as the theoretical yield. So in this example, we want to know the theoretical yield of manganese with 65 grams of calcium reacts with 57 grams of manganese 4 nitride. So in this example, it gives us the balanced chemical equation, and it also gives us the molar masses of our reactants and products. So again, what we're going to do is we're going to take the mass of calcium and manganese 4 nitride and convert it into moles of manganese to see which one produces the fewer moles of manganese. So we're going to need two equalities or 2 mole ratios. We know that 6 moles of calcium equal 3 moles of manganese, and we know 1 mole manganese 4 nitride equals 3 moles of manganese. So these are the two equalities or mole ratios we want to use. Now we can set up our train tracks. I'm going to set up 2 of them. So we're starting, first we'll do calcium, and then we'll do manganese 4 nitride. So we're going to convert mass to moles by dividing by the molar mass. Then we want to convert it to moles of manganese. So it's 6 moles of calcium gives us 3 moles of manganese. Since we're starting with moles of calcium, it goes on the bottom, and manganese goes on top. We do the same thing for manganese 4 nitride. We're going to divide by the molar mass to get the moles. Then we're going to convert it to moles of manganese. Here it's a 1 to 3 relationship. And now we can determine the moles of product produced by each reactant. And so in this example, manganese 4 nitride produces a fewer moles of product, so it's going to be our limiting reactant. So now we're going to convert the moles of manganese produced by the limiting reactant to get the theoretical yield. And of course, now we can disregard everything about calcium that we've calculated. So to go from moles to mass, we need to multiply by the molar mass. we get 42.5 grams of manganese. And again, this is the theoretical yield. So with percent yield, it's a kind of a ratio between the actual and theoretical yield. Kind of signifies how well you perform the reaction. Again, the way we find percent yield, we take the actual yield, which, as I said earlier, is the amount of product you actually obtain. So when you weigh your amount of mass of product, that's the actual yield. Now, in a textbook problem, the actual yield is going to be given to you in a problem. Unless you have to solve for the actual yield, then it would give you the percent yield, and you would have to solve for the actual yield. The theoretical yield is the amount calculated from the limiting reagent. That's what we've been doing in these last three examples, determining the theoretical yield based on the limiting reagent. Once we have both those numbers, we take actual over theoretical times 100. So the closer it is to 100%, the better you did your experiment. So here, for example, we have a certain experiment. The expected yield is 1.352 grams. The actual yield was 1.279. To determine the percent yield, you just simply take the actual over theoretical times 100. Again, the closer you are to 100, the better the experiment was performed. Now, if you go over 100%, that's very bad, because now you're saying you've obtained more mass than was what was possible based on your calculation. So either A, you made a wrong calculation, or B, there was some impurity in your product. And for most lab experiments, the common impurity is water. If people don't leave enough time to dry the product, water is a main impurity, and which will cause you to have a mass that's greater than your theoretical yield. So now we're going to look at a few problems involving percent yield. So here we have a reaction with phosphorus and iodine. We want to know what's the percent yield of the reaction if 28.2 grams of phosphorus triiodide is obtained from the reaction of 48 grams of iodine with excess phosphorus. So it tells us we performed this reaction. We produced 28.2 grams of phosphorus triiodide. This here is the actual yield. So we're not going to use this number until after we find the theoretical yield. So put this to the side and leave it for now. Now we have to use the other information to solve for the theoretical yield. So we use 48 grams of I2 with excess phosphorus. So since we use excess phosphorus, that tells us that I2 is the limiting reactant. So we're going to convert the mass of I2 into mass of phosphorus triiodide. So we need a few molar masses. We need the molar mass of I2, and we need the molar mass of phosphorus triiodide. Secondly, we're going to need the mole ratio, or the equality between I2 and PI3. So based on the balanced chemical equation, 3 moles of I2 equal 2 moles of PI3. Now, since the other reactant is in excess, we only have to do one calculation. We don't have to do the duplicate, because one is in excess. We know for sure that I2 is the limiting reactant. So I'll set up the train tracks. So we're starting with 48 grams of I2. First, we want to convert that to moles, so we divide by the molar mass of I2. And we convert that to moles of I2. Second step, we want to convert it to moles of PI3. So moles of I2 goes on the bottom. PI3 goes on top. Now you could do this all in one step if you wanted to, but I'm going to do it in 2 steps. And we get 0.126. Double check my work. Yep. Now we have the moles of moles of PI3. We're going to convert that to mass of phosphorus triiodide. 1 mole PI3. Molar mass goes on top. Now again, if you calculate the theoretical yield and you notice that the theoretical yield is less than your actual yield, you've done something wrong in calculating the theoretical yield. Theoretical yield should always be more than the actual yield. 51.9 grams of phosphorus triiodide. And again, this is called the theoretical yield. So now to calculate percent yield, we take the actual yield, which was given to us in the problem, divided by the theoretical yield times 100. And we get 54.3%. So that's the percent yield for this reaction. So one last problem involving percent yield that I wanted to show you is, so there's 2 types. One is calculate the percent yield, which we did on the previous example. The other one is it gives you the percent yield and it says what is the actual yield. So here, instead of giving us the actual yield and asking for the percent yield, it says, hey, we give you the percent yield, what would the actual yield be? And we're still using this problem involving phosphorus and iodine, gives us phosphorus iodide. But if you note something here, it gives us the mass of phosphorus and the mass of iodine. And the percent yield is 60%. So right now, this percent yield, we don't use it until after we find the theoretical yield. So for right now, put it to the side and don't look at it because it's going to confuse you. So just put it to the side. Just focus now on the mass of phosphorus and the mass of I2. So this is what we want to focus on right now. So from the mass of phosphorus and mass of I2, we need to determine the limiting reagent, and we need to determine the theoretical yield. So before we begin, again, the equation is balanced. Before we begin, we're going to need some molar masses. Molar mass of phosphorus, 31 grams. Molar mass of I2, We're also going to need some mole ratios. So for phosphorus, the phosphorus triiodide, it's 1 mole of phosphorus equals 4 moles of phosphorus triiodide. And for iodine, 6 moles of iodine equals 4 moles of phosphorus triiodide. So now we have our molar masses that we need. We have our mole ratios or equalities that we need. Now we're ready to determine which one is the limiting reactant. So we're going to do 2 sets of calculations because it gave us mass of both reactants. Again, we're starting with mass of phosphorus. We divide by the molar mass. Made a mistake. It should be P4. So it should be 124 grams per mole. So again, the mass goes on the bottom. Then we convert it to moles of Pi3. So 1 mole of P4 gives us 4 moles of Pi3. So there should be a 4 right there. We do the same thing for iodine. 68 grams of I2. Divide by the molar mass. And then convert to moles of Pi3. So 6 moles of I2 on the bottom because we're starting with I2 on the left, on top. And then we put 4 moles of Pi3. So now we get the moles produced by each reactant. We notice here that iodine produces the fewer moles of product. So iodine in this case is our limiting reagent. So now we can disregard everything about P4. Just put an X through that. And now we can convert moles of Pi3 into mass of Pi3. So we get 73.5 grams. Again, this should always be less than, oh, we don't know what our actual yield is, so. So this is our theoretical yield. But it wants us to calculate the actual yield. So what we're going to do is remember that percent yield equals actual over theoretical times 100. So if we're solving for actual yield, actual yield equals the percent yield times theoretical divided by 100. So this would be 60 times 73.5 divided by 100. Basically, you're taking 60% of 73.5. Then we get 44.1 grams of PI3 would be our actual yield.